Okay, in this lecture we are going to learn about covalent bonding and specifically try to write Lewis dot diagrams for these types of bonds. Now, before we get started, let's understand that when we deal with covalent bonding, we have to understand that covalent is different from what we've been doing. As I've been driving home, hopefully in class, covalent bonding, okay, is going to be dealing with nonmetals bonding with nonmetals. So if we take our staircase, okay, and it separates really the small atoms from the big atoms, we can see that these elements up to the right, from the visuals we talked about, are the smallest atoms. And these atoms off to the left down to the biggest atoms. Now, we already talked about the bonding between the big and the smalls that transfer electrons ionic. We've been through that. Now we're going to be specifically talking about covalent bonding. And as I alluded to before, if I had two people who are going to be holding a rope, all right, and they both are strong, which we say has a high electronegativity. Let's say this electronegativity is, I don't know, 2.2, and let's make this one 3.0. Okay? Well, these both are relatively high electronegativities, which means they both attract other people's or other atoms' electrons very well. So I think of electronegativity as a force, and these two have very high forces, or they have a great ability to pull in this rope. So if we have two people with their relative strengths pulling on a rope, they're going to be forced to share this rope. Nobody's strong enough to yank the rope away, so they share. But in this case, as we'll see today, they're sharing unequally, and this rope is going to be pulled closer to this person. Now, this rope represents valence electrons, or the electrons in the bond. So the pair of electrons that are being shared in a bond are being pulled closer here, but they're shared nonetheless. In ionic bonding, we had a transfer because it's kind of like myself holding on to a rope with my 3-year-old and saying, go, and pulling the rope, and I would yank the rope away from my son. I'd step over him as he's crying, say, who's your daddy? But no, I wouldn't do that. But of course, me pulling on the rope and taking the rope, I'd be acting like the nonmetal who's stronger, has a higher electronegativity, and my 2-year-old son, 3-year-old, would be the metal, and we'd have a transfer in ions. But here we're forced to share because all of these atoms in this area here have high electronegativity. It's important that you can look at the periodic table and understand the type of bond that exists. So nonmetals with nonmetals are forced to share. Metals and nonmetals have a transfer. Nonmetals share. So let's continue on this little journey and start showing how these things bond, and we can determine a lot of different information by just putting dots and sharing. Okay, so we're going to start this process with the next slide. So let's go there. So now we have hydrogen. Okay, and if you're working with me, you should be using the arrow button, the big arrow button, to move things around. So I'm going to make H2. So I'm going to throw one H here, and I'm going to put in one valence electron. Okay, then I bring another H into the play, and let's put this electron here, and let's put another electron here to show. Now the reason why I'm doing this is because this is 1s1, and this is 1s1. They both have the same number of electrons. In this case, they have the same valence electrons. And they all want to be like 1s2, which is helium. Okay, so I put the valence electrons out, and lo and behold, party people, I'm done. And how do I know I'm done? I'm done because I can count that hydrogen by sharing feels like it has 2, and this hydrogen by sharing feels like it has 2. And we could write this H with 1 dash. And that's the same thing. A dash represents a pair of electrons. And this is the bonding between hydrogen. Notice hydrogen is diatomic because it's a nice match. One H brings 1 electron, the other H brings another, and they both feel like they have 2. They both feel like they're filling their s orbital, and they both have the same stable configuration as helium by sharing. Now notice something here. They're both the same atom. Because they're both the same atom, they both have the same electronegativity. So if I write 2.2 for the electronegativity of hydrogen and hydrogen here, and I notice that, wow, if they both have the same strength, thinking about the tug of war scenario, I notice something very, very interesting. These electrons are going to be shared equally. So that's important. So this is sharing equally, and they're being shared equally because they have the same electronegativity. So equally, I can do this. Now we call this scenario where you share equally called a non-polar bond. Now the reason why it's non-polar is because each side of the bond is the same. Polarity or polar usually means that you have differences. If I was bipolar disorder is when you have certainly differences in your personality one day from the next. But if this is an H and this is the other H, and we're going to measure the differences from one side of the bond to the other, this side of the bond feels as much electron density as this side because these electrons are right down the middle, shared equally, because they have the same electronegativity. So we say that this compound, let's get rid of some stuff here, its bond polarity, and this is new, we would say that its bond polarity is nonpolar. It's a there's a nonpolar bond here because of the shared electrons being shared equally down the middle because they have the same electronegativity or force. Think of two twins that have the same environmental factors, same genetic disposition. Theoretically, both would be pulling on this rope and they'd be sharing that rope down the middle. Not sure if I drew identical twins, but you get the point. So it's non-polar. We're not going to do hybridization, molecular geometry, although we can do this with two atoms. It can only be linear. We're going to do that another day and add to this. All right? So this is what we're doing, is we're doing Lewis dot diagrams and figuring out the bond polarity. Let's go on to the next slide. Okay, so the next slide, make sure you're in the arrow here. I have two bromides. So here comes the, oops. Let's try to drag a bromide. Well, it looks like I can't do that. So I'm going to need a bromide, and I should fix that. So I'm going to write it there. So here's a Br, and here's a Br. Two of them. Let's see if this works. Good. Now each bromide has 7 valence electrons. It's a halogen. All halogens in the group 17 have 7 valence because they all have 5 electrons in their outer P's. So I put 7 here. And I'll put bromide. Another bromide also has 7 valence electrons. It's the same element. I'm just going to draw different colors to show whose initial valence electrons I'm starting with. In Lewis dot diagrams, we always put out the valence electrons, all the valence electrons, and then we start pairing up one bond. So there it is. And let's just put this nicey nice like this. And if you notice, by sharing, this bromide feels like it has 2. And this bromide feels like it has 2. Now you don't need the circles to do the Lewis dot diagrams. So if I take away my circles, this would be the correct Lewis dot diagram for the covalent bonding of bromide bonding to itself. If you notice something, I don't have brackets. I don't have charges. We're not transferring electrons. In our illustration, in our Lewis dot diagram, we're showing sharing. And they're forced to share because they both have high electronegativity for the things I've explained previously. But I like to put the circles in to show you that this one now feels like it has 8. This bromide feels like it has 8. And we call it feeling like 8 the octet rule. And of course the reason why we have the octet rule is because bromide, by gaining or feeling like it's sharing or gaining, will have the same stability as krypton. So they both want to become like a noble gas in terms of the electron configuration. So they both feel like they're gaining one, although they're not pulling one from the other. By sharing, they feel like that. So it's a nice combination, and you can see why bromide bonds to itself. Now I can write this another way. I can write Br, a single dash for the 2 bonds. Oh, I'm sorry, for the 2 electrons. Each bond is a dash. But when I do it this way, I have to be very careful that I write in the lone pairs of electrons that are not involved in the bonding. If I leave them out, this would be a wrong. So the dots that I drew above, This is a correct Lewis dot diagram. Circles are not required. And this one's also, I can use a dash in between to represent those pairs. But if I do it this way, I have to write in the lone pairs that are non-bonding. Okay? So the bond polarity, if you notice, this is the same element. They have the same electronegativity, so guess what? They're going to share equally. Therefore, each end of this covalent bond is going to feel the same. There's no poles, there's no difference, and the bond polarity is nonpolar. This is an example of another nonpolar covalent bond because of the equal sharing. I may not have drawn it correctly, but the electrons are right down the middle. And it makes sense why bromide is diatomic, right? Because it's easily a nice puzzle piece. This has 7, this has 7, and they come together very well. Moving on. Oxygen is another diatomic molecule. Now, why is it also? Does it both have 7? Well, if we go back to our reference table, we'll see that, oops, not that. If we go back to our reference table, we'll see that oxygen, let me get some of this stuff out of the way. Okay, oxygen is 2 away. So each oxygen wants to feel like it's gaining 2 electrons. So you can see that bromide wants to feel like it shares 1 more. It was 1 bond. Oxygen wants to share 2 more, so it may need a second bond. Let's go see if that's the case. So we're going to start with an oxygen. Hopefully this works. Yeah, this one works. I'll put out 2. Now you must, like we were doing ionic bonding, you notice you had to pull out as many as you needed. Notice I'm only pulling out 2 because these make molecules, definite shape, definite number. Okay. Now with these 2 out, as I've done before, I always put out the valence electrons. We should know that oxygen has 6. It's in group 16. We always put out all the valence electrons like you did with ionic Lewis dot diagrams. We do the same thing. So this has 6, and this has 6. All right. Now, the first step, once you have all your valence electrons out, is make 1 bond. So put 1 of each. Pair them up. I'm going to put them right down the middle because, well, I'm going to put the bond this way. So I've got 1 bond between these 2. Now, you may say, well, good. We put 1 of each electrons, and that's a bond. Is that good? Well, we have to evaluate our drawing. Remember the octet rule. Because oxygen is in row 2, or period 2, it wants to have 8 electrons. As I showed before, it wants to feel like it's gaining 2. Right now, it's only feel like it's gaining 1. And we can check to see how that is working by this oxygen, by just sharing 1 more, the way that I've drawn it. Feels like it has 2, 4, 6, 7. There's only 7 electrons. This oxygen, by having 1 bond and sharing 1 of its own with somebody else's oxygen's electron valence, feels like it has 1, 2, 3, 4, 5, 6, 7. So this is not going to work. Oxygen, okay, wants to feel like it has 8 in its valence shell to fill it, as I talked about. So 7's not going to want to work. So the only thing we can do at this point is we can put another pair together. And that's the thing. So if the first bond doesn't complete the octet, we have to pair up another bond. Now I kind of alluded to this already. Oxygen wants to feel like it has 2 more electrons. So what it does is it makes something called a double bond. And you can check with your circles here. This oxygen feels like it has 2, 4, 6, 8. This oxygen also feels like it has 8. So oxygen gets stable by using another oxygen's pair of electrons. And collectively, they bond this way. Now, oxygen has a double bond. So if I was to draw it, a Lewis dot diagram another way, I can draw 2 dashes. Notice there's 2 dashes. Each dash is a pair of electrons. And just like I said before, if you do it this way, you have to draw the lone pairs. So these have 4 lone pairs left. This has 4 lone pairs left. And this is the Lewis dot diagram, this or this, okay, without the circles. If you put the circles in, it's not wrong, of oxygen. And you can see that you should be able to figure out that oxygen is O2. And our first activity in bonding, people said, oh, Mr. Grotsky, how'd you know O2 was double bonded to an O? Now you can do that. You can see how many bonds exist and how these structures look like by doing what we're doing. Okay? Now, what's the bond polarity? I hope you guessed it's nonpolar. Why is it nonpolar? Because it's the same element bonded to itself. So therefore, they're sharing electrons equally, and each side of the bond feels the same amount of electrons because of that equal distribution, equal sharing of electrons. Nothing else we can do yet. Okay, going forward, we have N2. All right, so we do the same thing. We take N, we take another N. Now I'm taking only 2 because the molecule only has 2. All right, it's an exact molecule. Now I put out the valence electrons. Nitrogen has 5. It's in group 15, 1s2, 2s2, 2p3. It has 5 valence electrons. So I'll just do that. This, we'll do red. This nitrogen also has 5. When you do Lewis dot diagrams, you don't have to do circles and reds and and X's and dots, but it's a nice way to first learn. So the first step, make a bond. Evaluate to see if you satisfy the octet rule. Nitrogen wants to feel like it has 8 as well. All nonmetals want to gain enough electrons to become 8. If you noticed in your other activity, nitrogen likes to become -3 when it's an ion. It's gaining 3 electrons. Oxygen likes to become -2. Bromide likes to become -1. Is there some hints here in all of this? There certainly is. Let's continue. All right. So as we go forward in this process, I'm going to evaluate my nitrogen. This nitrogen feels like it has, let's see, 2, 4, 6, nowhere close to 8. This nitrogen feels like it has 2, 4, 6, nowhere close to 8. So what I'm going to do is make another bond. Pair them up. That's all you can do. Put the valence electrons out and start pairing them up and start evaluating. This one feels like it has 2, 4, 6, 7. This one, it feels like it has 2, 4, 6, 7. Still no good. So all you can do after you vet is add, guess what? Another bond. And nitrogen, okay, I'm going to move the lone pairs over here. If you don't do that, it's okay. I'm just showing that that's how they would really work in nature, but it's okay if you left them anywhere. Bottom line is we put 3 bonds together. Let's evaluate. This has 2, 4, 6, 8. This nitrogen feels like it has 2, 4, 6, 8. My gosh, we've onto something here. And nitrogen triple bonds with itself in nature. You may wonder why 80% of the air is nitrogen, yet we don't really use it. It goes in our system and it comes out of our system. We breathe in nitrogen, breathe it out. We don't metabolize it. Well, one of the reasons is it's got a high bond energy. With triple bonds, the bond energy is through the roof. I don't know if Mr. Valley or your biology teacher talked about fixing nitrogen. Living plants need nitrogen. We need nitrogen. But we can't use it bonded to itself like this. So we have to fix it. Now, legumes will take the nitrogen of in the air and convert it into a nitrogen that has only one bond, like ammonia. Plants need nitrogen, but they can't use the nitrogen in the air because of the triple bond. It makes nitrogen pretty unreactive to us. We take in nitrogen, but we can't get it from the atmosphere and use it because of the same problem. So plants, a lot of time, you can spray ammonia on plants or a byproduct of ammonia, and ammonia is single bonds between the ends here. And this is called fixed nitrogen. Legumes do that for the grass. So important fertilizer is to take nitrogen and break it into a single bond scenario as opposed to the triple bond with itself. A little background that may be useful to you one day. But in any case, can you guess the bond polarity? Is there a pattern here? Absolutely, the bond polarity is non-polar because those electrons, again, are being shared right down the middle. These both have the same electronegativity. Okay, let's continue with this game of fun. Let's do methane. Okay, it's CH4. You name me some, Mr. Grodsky. How does this look? How do I know the shape and who's going to be the middle atom? Well, people will do different laws, but I think of it this way. if you put carbon here and you try to make this molecule this way, you probably can guess that this is probably not going to work. And let me explain. Carbon has 4 valence electrons. And as you can guess, because it has 4 valence electrons, doesn't it need to feel like it's sharing 4 more electrons to have that octet number, have that 8? And your answer is yes. So carbon can make 4 bonds. Okay, up to 4 bonds. So if I was to put a hydrogen here, hydrogen has a valence electron. Can hydrogen bond over here? Let's just pretend that you did that. Let's say you said, oh, I'm just going to put some bonds out here because I'm just bond crazy. Well, if you do this, think with me for a second. Okay, this carbon is sharing these electrons, and it's not 8 yet, but it will be. If this hydrogen is feeling it has 2, how can it bond over here? Hydrogen has to only have 2 electrons. So if hydrogen is making a bond with carbon over here, it can't bond with hydrogen. See, hydrogen is a terminal atom. It only makes 1 bond because it has 1 valence electron and it only needs 1 more. Your halogens are also terminal. Look at fluorine or bromide or iodine. They have 7, so all they need is what? 1 more electron, and they are also a terminal atom. But atoms that have what? Anything in between can have multiples. So all of this makes no sense. So clearly, carbon has to be in the middle because it can bond to more things. Hydrogen is terminal, so it has to be on the outside because it only makes 1 bond with only having 1 valence electron. So let's get these out of the way. And let's move these over. Okay, let's bring carbon in the middle. Carbon has 4 valence electrons. Put out all the valence electrons. Each H can make 1 bond terminally with the carbon. That's it. So it's clear to see that you would have 4 of these, and I'm telling it's 4. Each hydrogen has 4. And looky here. Let's evaluate. This carbon feels like it has 8, which is good. This feels like it has 2. Mr. Grotsky, that's not the octet rule. Well, wait a minute, party person. If you look at hydrogen, hydrogen's not going to follow the octet rule because it wants to feel like it has 2. There's only 2 electrons in the first row. So by gaining or feeling like it gains 1, it's going to feel like it has the same configuration that's as stable as helium. So it wants to have 2. All right. So as we go through this, oh, Christmas, what am I doing? Go through this. Here I am. So each hydrogen feels like it has 2. You don't need circles. This is the correct Lewis dot diagram. Of course, I could write it this way. Carbon, a dash to H in every direction. And here we go. Notice there's no lone pairs, so this is also an acceptable example of a Lewis dot diagram. Now, based on New York State Regents laws, we would say that hydrogen and carbon have 2 different electronegativities. Okay? And I'll explain in detail as we get in class, but hydrogen and carbon are not the same elements. Look at all of these guys. These are all the same elements bonded to each other. So they all were nonpolar because they all were sharing equally, whether it's a double or a triple bond, because they had the same attraction for other people's electrons. And these electrons are pulled down the middle. But in this case, according to New York State, because, well, that's what we're dealing with, hydrogen's 2.2, carbon's 2.6. This pair is not being shared exactly equally. It's going to be a little bit pulled closer, not a lot, but pulled a little bit closer to the carbon. Why? Because a carbon has a higher electronegativity, and therefore this side of the bond feels the negatives more than this side. So we would say that this side of the bond is a little bit partial negative, this side's a little bit partial positive. So we call this a polar bond because of unequal sharing. In the other examples, they were sharing equally because they were the same nonmetal, same electronegativity. In this example, they are different, therefore they have different attractions. Now, I will tell those that are outside the New York State regions that a hydrogen and carbon has such a similar electronegativity, around zero point 0.4 difference, that most textbooks, most courses, most everybody else besides New York State considers the carbon to hydrogen to be a nonpolar bond. But sticking to New York State regions, this is a polar bond because they have two different electronegativities, and you should know that they're being shared unequally because the stronger one pulls the rope a little closer and this side feels it a little more. Okay, moving forward. CH3I. Okay, I want to kind of jump around. Let's go, let's do CO2. And this will be the last one I do. I think you got enough to continue doing this. Okay, so carbon. I can do this. Bring out a carbon. So Mr. Grotsky, who's in the middle? Well, I know carbon can make 4 bonds. Oxygen can make 2. So to work it out, you probably see the one that can make more bonds is usually in the middle. Some people say the least electronegative atom is in the middle, but I like to look at how many bonds it can make. Carbon can make 4. Each oxygen makes 2. So this is how I'm going to set this up. I've got all this space, but I'm cramping over here. Yeah. Okay. Now, Mr. Grotsky, how do you know that it's not this way and that way? I'm going to draw it linear, and I'll explain why in a second. Okay? Here comes carbon with its 4 valence electrons. I'm just going to throw them out there. All you do is throw them out there. Okay? Oxygen has its 6, so throw out the 6. First step, put your atoms together. If it's more than 2, try to put the least electronegative atom in the middle, or the one that has more bonds. That's a good way to do it. And as you do this and have more experience, it'll be clear who goes in the middle. Just trust me on that. All right, so we keep going here. Okay. Now, first step, make 1 bond at least, right? So take 1 here and 1 here. Take 1 here and 1 here. Let's evaluate. What do we have? 2, 4, 6, 7. No good. Oxygen, 2, 4, 6, 7. And the carbon, right? The carbon you have to evaluate too has 2, 4, 6. Not going to work. Everybody here wants to feel like they have 8. We don't have a hydrogen. So the only thing you do is add another bond. Yeah, double bond. Here, and add another one here. And now let's evaluate. This carbon, by sharing, feels like it has 8. Very good. This oxygen, by sharing 2, feels like it has 8. And so does this oxygen. Boom, there it is. So carbon can be drawn this way. Double bond to an O, put in the lone pairs. Double bond to another O, put in the lone pairs. This is the same. You don't need the circles. Now, Mr. Grotsky, how do you know it's linear? The shape is linear. Well, I'll tell you why. Oxygen doesn't have any lone pairs up top. All of its lone pairs are being used in bonds. If it had a lone pair of electrons up top, these electrons would bend this downward. So I know it's linear, and we're going to get into this shaping next week. Right now, it's the basics. Now, the question is, what kind of bond polarity do I have? This is the correct Lewis dot diagram showing the sharing, but what kind of bond polarity do I have? Well, you guessed it. This is 2 different nonmetals with very different electronegativities. They're both high. This one's about 3.5, and this is about 2.6. Okay? So they're very different, farther than the 0.4 we talked about. So this is going to be a polar covalent bond. Now, I really don't have to put covalent bond because ionic compounds never make polar bonds because they're made up of ions stuck in a crystal, and those ions are not free to move to create differences. Every side of a crystal is the same as another because the ions are equally interdispersed. What makes a polar bond between the O, let's just draw one, and I'll be finishing up on this, is the C and the O, just drawing one side, is that the O is more electronegative, so these pairs of electrons, honestly, between them are being pulled closer. Okay, I'll do it on this side. Being pulled closer to the oxygen than they are to the carbon. So we have an unequal sharing, and this creates more electron density on this side of the bond. So therefore, this side of the bond feels a little bit negative. This side feels a little bit positive. Now, these aren't complete negatives and positives because there's not a what? complete transfer. Okay? It's being shared unequally. So we like to write partial charges. Partial positive, partial negative. We'll talk more about that. But that's what you need to continue on the ditto, the worksheet, front and back. I have the key posted. Good luck. Enjoy the rest of your 3-day weekend, if it is a 3-day weekend, because I'm making this for eternity. Thanks.